Here I am sitting down with Corrinne Yu, who's the principal engine programmer for 343 Industries. Talk about how you got involved and what some of the first projects were that you got to be a part of.
I first started working for the lead programmer for the King Quest series, Poseidon, and I also worked with the Frogger programmer John Harris. And so I was basically doing a lot of programming with a lot of the early Apple II adventure games while putting together my first 3D engine. So I started writing 3D engines actually before there were any 3D engines, and I was writing software rasterizers back then. So in terms of the 3D engine industry part, I was basically shopping around my 3D engines to companies like GD Interactive, way before there were any 3D cards and so on. Some of my super early projects would be for actually Apple. I wrote one of the earliest demos for Apple QuickDraw 3D, so it's been with 3D engine and 3D engine game development since the very beginning, before there were any 3D cards.
Wow. So clearly, talking about John Harris with the original Frogger, you've been around for a long, long time. What was game development like from a community perspective back then?
Game development actually have changed a lot. The technology that we develop is so much more advanced now than it used to be. The game industry used to be a lot smaller, and it used to be a lot more hobbyist. It's certainly less of a corporate, less of a professional environment in both a good sense and a bad sense. And a lot of it, you pretty much have to blaze your own path with every algorithm that you invent or develop. It's there are a lot of it about the old days that I miss, and yet there's a lot of it about the current days and new days that I really enjoy, that I'm really glad that we're over those hurdles again. I would say back in the old days, there is a lot more of reinventing the wheel. I see a lot more people basically developing and coming up with the same thing. It's not so much there actually were a huge amount of sharing. The community was very open, and all the 3D engines programmers know each other very well. We share a lot, but then we pretty much have to reinvent everything from scratch. And now I think there are a lot more basic algorithms that people can start with and then develop the engines forward.
So is this something you always knew as a kid you wanted to do? Did you always toy with computers or programming?
I've loved programming a computer ever since I saw one, I touched one. My first computer I programmed on was the Apple II. And back then, it was before the personal computer revolution, so a lot of it was that basically go to universities and try to borrow time, on the really big mainframes. I also tried to work for colleges as well as work for scientific research communities where they have computers and program things for them. So one of the first professional jobs I have actually programmed on punch cards on the Fortran 77. So it's definitely. I loved it so much that I just went out of my way to seek out opportunities where I can either do it for free or do it for a job. And nowadays, when people think about programming as a hobby, it was just like the computer's already at school at home. I just want to go learn programming. But back then, when we were a hobbyist and when I was a hobbyist, it was like you don't have a computer, so you love it so much you actually have to go your way to go find one and then go program on it. And then eventually, the personal computer revolution happens, and now we have all these personal computers available for anyone to learn to program, which I think is fantastic.
And you've gotten to work with some of the best in the industry. We were talking, you worked with Carmack.
Oh, no. There was actually, we were on the same graphics advisory board together. I've worked with a lot of really fantastic programmers, but but then in terms of all the volunteer activity that I do for designing 3D APIs, for example, like the direct 3D APIs and so forth, I work with very intelligent, very experienced, very important programmers in the 3D engine community that I'm really grateful to have an opportunity to kind of design APIs with them and so on. So yeah, Carmack was one of the people who kept popping up for a lot of these various 3D API committees that I'm on and so on. So it's certainly a pleasure, and it's a good education experience to be working with such great minds.
And we talk about software, but let's also talk about hardware. Clearly, consoles were very different back in the day with cartridges and the 3DO with CD, I guess not that different from today. But what was it like to program for some of the older consoles versus like the Xbox 360 nowadays?
Tools and compilers certainly is the really big difference. I was actually programming for the 3DO launch, so therefore, and then back then, console launches have like way fewer tools. We were basically making our own compilers for the 3DO. Of course, there's no such thing like as even a library, but the fact that we actually have to generate the code to generate the code, I thought that part was pretty funny. The other thing too was that the 3DO never was a real 3D accelerator, so was writing the engine. They basically turn a sprite acceleration engine into a 3D acceleration engine. So versus now with Xbox 360 especially, the compiling tools, development tools, languages, profiling tools, it's just a world of difference. There is still a lot of room for innovation on the Xbox 360 in terms of brand new techniques that people can develop for it, but all the tools to help you come up with these techniques are all there. All the tools to help you drill down of why can't I make this real time because it's so slow? Why is it so slow? The profiling tools back in the old days certainly were much worse than it is now.
So what were some of your favorite older languages to program on?
I think I've been using C for quite a while. There are some variants of the machine code or the assembly language or the shader assembly code that it's not so much that I'm very fond of it, was that I was very fond of all the tricks I was able to pull with it. But then once I did something in this low level hardware knowledge, that the exact way of doing this doesn't exactly port over to new hardware. So I guess with the first PSX, there was the asymmetrical UV pipeline and then a fixed math stuff. It was not like I would love to program fixed mathematics, but then fixed point mathematics, but then programming all the super clever ways to maximize precision and make the fixed point mathematics go faster. I thought that part of it was just fun in the way that Tetris is fun, as opposed to just making little puzzle pieces. But I would say that C has been a language that has been used in game development for quite a while and will probably continue to be so.
Have there been any languages that were just a disaster, that just were so tough to program on, or just more battles than there were victories?
I think game development is a really good sieve for that sort of thing, because as soon as a language or a tool is not useful, you just drop it right away, because shipping a great game and engine is like the ultimate goal. So I would say in my experience that, yeah, I've always on my own time trying out new languages and experiment with new languages and stuff, but I would never say that I've used this language and it was such a disaster and we carried this disaster all the way to the end. So therefore we don't have a lot of real sob story regarding horrible languages and stuff. I guess there's some stories about compilers and compiling tools or the code they generate, but they weren't really so much as dreadful tragedy, but just simple challenges to overcome.
So what are some of the misconceptions? I'm a consumer. I don't develop games.
Yeah.
Sometimes I run across a bug and I'm like, oh, why did this happen? Or why is this happening? What are some of the misconceptions from consumers that they have about maybe game development?
Well, the actually two questions I see here. One of them is, where do bugs come from? And then the other one is the misconception that people may have about game development. And as a person who wants to ship games, that is a very enjoyable experience for people. I don't so much as want to explain why there are bugs, as in I actually take the consumer side. I get mad or embarrassed if there is a bug that I didn't catch, we didn't catch, and we didn't fix, and just beat myself over the head on it. So the reverse answer to that is that when I'm near the end of the last milestone or deadline on a project, what I do is I try to get my work done ahead of time so I can spend all my time just playing my own game, just going through the same level again and again and again. And then also as a programmer, I know how to break it. I know where it would perform the worst. I know where I haven't so I would know exactly how to break my own black box. So I would go out my way to go to the worst place situation where, this lighting algorithm would totally work, but I'm going to make everything almost totally parallel, and I know that's going to really stress the system. So it's that I think bugs are unforgivable. I think lighting artifact and graphics artifacts are unforgivable. I guess a misconception would be maybe people don't understand how challenging and difficult it is to never have it, because it's not a misconception. It's that the hardware is basically have a fixed number of bits of precision. I mean, algorithm is a perfect world. Algorithm is a continuous function. It is, continuous hierarchical, deeper and deeper level of precision. I guess that there is like arbitrary precision mathematics, but that also takes the hours and days to finish running too. I guess it's that there's sometimes they're full-blown bugs, and sometimes there's some graphics and engine things in which you really, really do your best, but you're running on a system that ultimately have a finite number of bits, and ultimately that is the best you can do. You just have to let go. You just have to ship it. So when people are saying, "Oh, I can't believe that if I do this really obscure thing that only happened 1 in 10,000 times, I can, see." The lighting, this 1 pixel over, it should be blacker but a little bit whiter, that kind of thing. It's like most of us, we've done our best. We do the best that we can given the time constraint we have, and so it's not that we don't care. It's that but at the same time we need to work harder. It's not like, well, okay, this is the last game I ship. Maybe in next game I should figure out mathematics to see what other tricks I can to improve precision even greater. So I guess that answers the question about why do I see bugs in games or graphical bugs, and also misconception about there can potentially be a lot of misconception about game development. I suppose is that they may that one misconception could be just how most of the time people would think that would be developing and implementing the new graphics algorithms, when in fact when you've been a practicing veteran for a very long time, you know that you kind of have to cut down how much time you actually spend implementing your features and spend the rest of your time basically doing vertical slices of all the degenerate cases of where your algorithms may break or can break, and then supporting these algorithms all the way through the end. So one misconception could be that people may misunderstand what a huge gap there is between a short little 3D engine demo of a technique versus that technique being applied all the way through to the end of a complete game with 20 or 30 or 40 levels.
So is programming easier today with the amount of tools that you have, or is it more difficult than it was back in the day? Part of me thinks with the competition, you can't get away with as much as you did back in the day, but with the tools, maybe it's easier?
I think it is easier. It is easier to narrow down what's wrong. We've also gotten a lot better and better with techniques on how to narrow down a lot of these stuff. So it's, I think I would say that the answer is that it is easier, but that at the same time, when it's easier now, we want to do fancier and fancier things. So by the fancier things that we do, that causes things to become more complex again. So the things that would make things easier back in the old days was that the systems, the combination systems are relatively simple. Now the combination of system is really complex. Now we have a lot of systems that actually operate in completely different spaces, like frequency space versus like spatial space. And then all of that is supposed to eventually generate the same image together. Also the divergence of lighting techniques, right? Because before you can pretty much just program an engine with just one algorithm, what you choose to do with lighting, and then now we basically have like an explosion of things in which the end result is still to generate what the color of that lit pixel is on the screen, but you have a combination of a whole bunch of algorithms that actually materially and physically have different properties, and to have them always generate the same thing, same time all the time, and also the large numbers of permutation of primitives too. Back then, I guess you can just base your game on just simple. Okay, I've got just simple polygonal objects. But now you basically have to have a uniform rendered world with, some of your objects are polygons. Some of your objects are parametrically generated, parametric surfaces or subdivision surfaces. Some of them is participating media, some of them are volume objects. And yet all of these objects have to interact in lighting and also in simulation in the real way at the same time, but the mathematics to render them, to compute them, to simulate them, they are totally different. And for that to remain seamless all the time, I think that is a lot harder nowadays than before, when the number of permutations of primitives and materials too. Back then, material is the texture that you apply on it. Now again is explosion of material. Some of them are translucent, some of them are not translucent, and then some of them subsurface scatter, some of them don't subsurface scatter, and they all have different refractance, and they're all supposed to eventually, again, look like it is in the same world again, but they are not, like mathematically they're not, and you have to unify everything together. I guess one of the most interesting things, in fact, is now we start dealing with media in which it is a non-uniform media, and by that I meant that not the whole thing is solid, not the whole thing is liquid, but where the composition of the material inside and outside is actually composed, of different state of matter, and yet the continuity of the lighting has to be continuous within this material, right? So that is a lot more complex of a problem to solve than the problems we have to solve back then.
Yeah, I would say so. Okay, so now you program for the Xbox 360. How is that? How is that?
It's wonderful.
Console? Yeah, tell me a little bit about it.
It's got very good development tools. It's got very good profiling tools. I really love that, I can drill down, I can debug on a per pixel basis of like, how does this pixel get to this color from the beginning to the end? I love that. I love that I'm able to drill down to what is taking the most time where in this different piece of hardware, the GPU or the CPU on which thread. I love, what is going on with the texture samplers. It just this huge number of tools that I have to do detective work of just basically how I can squeeze the last bit of performance, how I can squeeze the last bit of, The thing is, the squeezing of performance, the whole point of that is to do a new algorithm, because we keep thinking, okay, we'd love to do this lighting algorithm, we'd love to do the simulation of this technique, but it'll be too slow. But the more you squeeze a performance out of it, then all of a sudden things that were not possible become possible, or just the whole flexibility. It's really funny that everyone was like waiting for like the Larrabee or like a next gen, PC GPU to allow them to do very flexible programming. But what I love about Xbox 360 and really is equivalent class is that the textures are basically your digital signal processing input output units. It's like they can be whatever it is that I want. So I really love how, in general, how flexible the texture formats are, and that using these texture formats I can do a lot of really neat things. Of course, with DX11 there is like a huge, explosion of flexibility right there too, and really we're looking forward to that. So I would say that Xbox 360 is like a toy. It's a toy that hasn't been so brand new. It's been out for a while, but it's a toy that I don't think most game programmers or game developers or engine developers have fully exploited all the things that can be done with that too, especially with thinking of the idea, a texture is not texture. A texture is just, signal inputs. A texture is just, user-definable function. It can be anything you want it to be. And I thought that aspect of itself was just exciting.
So what kind of programming languages do you use now when you're writing stuff for the Xbox 360?
Use C and C++, and with shaders. I use XLSL as well as microcode. In fact, I always program and think in terms of, there's a lot of embedded microcode actually in my XLSL. In fact, there's XLSL mostly because to keep the code readable, because if the whole thing is microcode, then it becomes, pretty difficult to reprogram for other programmers. But whenever I debug, there's two modes. You can either look at it in XLSL mode or you can look at it in microcode mode. Most of the time when I'm debugging for performance or for precision, I always switch over to microcode anyway. So I would say I am in microcode quite a bit. And the C and C++ I development tool I use is Visual Studio, and it's come a long way since. It's got a lot of really neat features. So it's so far I really love the development tools. It certainly can be better, but it's been pretty good.
So now we're going to switch gears a little bit. I have some questions here from some of our Channel 9 forum members. Now this one comes from Bass. He says, can you talk a little bit about the mathematics of rendering?
Well, rendering and graphics engine actually use a huge number of fields of mathematics. Fundamentally, it's got the basic 3D transforms and projection matrix and so on. That's the basic part. But at the same time, with lighting, there is a lot of the integral part of calculus, because we're basically integrating over surface areas of all the light contributions. And then with a simulation like soft body and so on, there's finite element analysis, which is used quite a bit. Actually, finite element analysis is actually even good for things like heat transfer and so on, like that too. So, and then since there is such a deep relationship between heat waves and light behavior and so on, so a lot of I guess like geothermal mathematics turn out to become very applicable to like light mathematics. There's a lot of very interesting parallel there. There's a lot of frequency space mathematics, because a lot frequency space mathematics used in rendering, because as it turns out there are quite a few of the computation that is complex in spatial, that when you move into frequency space, then it becomes a simpler things to solve, or that you can do like level of detail based on by cutting down on the frequencies, you can have like a low level versus a high level thing. So it is a really exciting field of programming, because it covers such a wide area of mathematics. So it's not, you're not bored doing just, oh my gosh, I'm just multiplying matrices all the time. I get to do all kinds of other neat mathematics. I think that geometric algebra is getting a lot of attention right now, and it's interesting in the way that it leads to new algorithm development and new insight, into things like animation. It's not necessarily a very memory efficient field of mathematics to implement geometric algebra directly, because you can't control basically how many number of dimensions it permutes into. But it's a really good way of using that to derive your algorithm, then reprogram that algorithm into just basically normal geometric transforms afterwards, and so it controls the amount of memory that you use. So yeah, there are lots and lots of fields of mathematics that we do use to generate 3D engines.
So this question comes from Androidy. Androidy is asking you, why don't we see engine companies putting effort on engines that would allow easier development of entirely new kinds of 3D games? The old-fashioned ideas like levels and loading stages.
Well, I guess what's interesting is that people think of levels as basically what is the artifact of level, which is that they're waiting for the levels to start, and then there's obviously a stopping point, and they have to load again. And I think that there's something fundamentally different. Well, I guess there is about games in which, okay, I'm not really stopping now, I'm going continuously into this world. There's the game design answer for that, and there's also the programming answer for that. For game design answer, I've actually worked on quite a few games in which I've worked really hard for a game in which we can just continuously run on and on and on. But as a gameplay thing, it turns out to be unsatisfying because people didn't have a feel sense of accomplishment and finality. When it's like, I've done this, I'm still going, where's my reward, where's that feeling? Or I've been at my chair all day, when do I get up and take a break? People need to actually be paced out to be like, okay, now it's time for me to get up. In fact, I think there's some video games now that actually made the place like, you've been playing this for about 5 hours, there's time for you to stop and go get a real life.
Because I think we've lost some gamers that haven't gotten up, right?
So that's the game design part of it, which is that after experimenting with people playing these games, we've actually noticed for a huge number of game style, this actually decreases their enjoyment. So even though technologically we could support it, just for game design reasons, we decide not to. The second thing about levels is that as a programmer, I never think of levels as something that is specific, as in I never program something so specific as an engine developer that can easily switch over to, say an open world kind of engine. And what I mean by that is that I think of levels really as a subset of the visibility problem, which is that what is possibly visible within that given range of time, given the speed that you or the third-person camera can run in, and given the range of things that can happen. I think there's a way to program 3D engines in which you don't have that reliability built in, so you can easily switch between the two. But I would say that people think that it'll be great if every one of my game, have no levels. But if they actually start, hitting every one of the games, and it doesn't actually give them that dramatic, level ending, that it in fact does take away a lot from their enjoyment. There's certainly limitation for what you can finish streaming from the DVD onto your console, but at the same time it's more to it than that is the reason why we have levels in the first place. Sometimes a lot of it is for game design reasons. And the other thing too is that the other good thing about building a 3D engine without built into the idea of level 2 is that way you can also increase and decrease your detail, and your detail can be geometric complexity, or your detail can be length of material shader, in which you can be like, well, in this close-up areas I can have much greater geometric complexity with much more material complexity, and now in this area I have a farther view distance, so I would sacrifice some material complexity or some geometric complexity for giving a feeling of an open wide world, that kind of thing. I mean, also with visible AI too. It's like sometimes I want a feeling of like a big giant troops coming at me. So maybe the AI detail of the farthest AI enemy is not as detailed, and sometimes you want to give the feeling of an NPC that I really emote with and act very intelligent and protect me, and then you would basically focus a lot of CPUs onto that AI that's really close to you, or a lot of actions that this AI is doing. So I think the idea of like a fixed size level is an antiquated concept, but I think levels in general is a really good device for a game designer to pace the sense of accomplishment and achievement the game player can enjoy.
Now we're going to take a question from Leo Davidson. Do you see FPGA add-on cards becoming useful or popular for gaming at any point, or is the niche that they fill be better suited to the newer general purpose GPUs that we have today?
I think there is a place for either a real field programmable kind of chip for some part of a 3D engine, and I think what could be kind of interesting actually would be something in which I've got some specialized texture caching algorithm that can be changed after the part is already shipped. I mean, part of it is that we are improving how we fetch texture, and also the kind of textures that we're going to have and how we're going to use these textures. I think first of all, there are multiple trends in 3D engine. One of them is that we're getting away from just pure polygonal objects. So we're going to have to start fetching textures for things that in which we would have a volume dimension to it, and that behavior is going to be a little bit different. The other thing is also what sparse texture can bring to us, and that field is just beginning to explode right now with the kind of things that we're developing algorithmically and so on. So the kind of texture cache customization, which hasn't been a real problem before. It is a real problem in the sense that texture fetching has always been a performance bottleneck for us. So we just basically want faster texture fetching, and 3D hardware and eventually consoles will respond by basically giving us this specifically burnt way of caching our textures and caching our samplers in such a way we can get the exact kind of granularity of what we typically expect with kind of a current generation of 3D engine. But what would be really interesting is that, but what if we start, deviating from that way of fetching textures, or that way of, engine programming? Then does it mean that for every iteration of algorithm, which going to pretty much grows by Moore's law instead of grows linearly, that they have to ship a new piece in order to, optimize the texture, cache performance? And I think it will be really interesting for the texture fetching and texture caching part of it to be semi-programmable, so we as programmers can actually send an update to it and then have it, adjust the best case scenario for us, reading from our samplers. I think that could be a potential use for that. And so, yeah.
Now, Creamfilling 512 says, Halo games use their own proprietary game engine, yet so many games, including AAA games, use a licensed engine like Unreal. What's the advantage or disadvantage to rolling your own engine in this day and age?
I think the advantage of owning your code base and owning, I guess, your graphics pipeline, rendering pipeline, and your engine pipeline is the full flexibility to advance to the stage of technology you think it should be. I think you are in some ways always held back. Not so much as there's exactly one feature, it will be impossible you program from another new engine, but a lot of it could be just that relationship between the format is stored on the DVD, streaming it off the DVD, having that DVD format be in the CPU RAM somewhere, and then also have that format be in the video memory somewhere. The Xbox 360 is a highly efficient system with some really interesting, memory mapping, for the video memory that should be exploited, can be exploited. And if you use a custom engine, for example, you can actually, program your metadata and your data format on the DVD in such a way it just does a block load blit into the format that your engine exactly need and want, into the graphics hardware. If it is somebody else's engine, you can't do that kind of optimization, as easily. So that would be one of many advantages.
So you prefer working on?
I really like, having, a code base that we own. That's very, very good.
Now this question comes from Baz. Do you think there's ever a future for managed languages in game development for games like first-person shooters where speed is everything? It's interesting because there is the C and C++ is a really veteran language that has a lot of good optimization built into it already in the compiler because it's got so many years of generating code for it. So it's going to be around for a very long time and probably isn't going to go away. But I think there is a very good place for not just any managed language, but functional languages. I've been playing with the F# quite a bit. It's really exciting. It's a very good language for doing mathematics programming. And the interesting thing about functional languages, not so much as managed language per se, is the idea of closure and the idea of a clean concept of a function as an object. And the reason why that's very important is because we're really entering into a multi-core, many-core world. We're also entering into an asymmetrical core world. The GPU start doing what CPU does, and CPU starting what GPU does, and all of this is happening in parallel and happening asynchronously. With a C and C++ language, it's not built very well for that sort of massive parallelization. But when you can start encapsulating, your function and objects, when you can start, encapsulating, functional and data decomposition into, tiny little bits and be able to send it off into whatever processors are free, that is something that I'm really looking forward to with some of the new language developments. Now the question is, would that be a full-blown, functional language like F# or something, or would it be something where is a new version of C, which is
will be so different that it is completely foreign to what we understand, C++ to be. I don't know yet. I'm keeping my bets, on everything. So I'm programming C++, I'm programming F#. I'm also giving, my input to whatever language, experts or language designers would listen. And I think that what I will see is probably C evolving into a language that can do, a lot of what the slower managed code can do, but in a much more efficient form. I think we're going to see that sort of hybrid, and I'm kind of really looking forward to it, because in order for us to move into the multi-core, many-core world, we do need quite a few language improvements together.
Great. And Charles says, what's on your mind in terms of the biggest problems facing gaming engineers as we head into both a massively concurrent and distributed future? Distribution is a problem on a single machine too, just less latency given the proximity of execution cores and memory.
Well, I think there is actually a huge amount of promise that's held by having so many extra processes and having all these processes do a lot of different things. I think we have to completely rethink a lot of our old algorithms, because I think a lot of our old algorithms still think relatively sequentially, and when it does decompose, it decomposes in a very macro functional form, like, oh, this is my game thread, this is my rendering thread. I think that most people in the past have been developing algorithms not really based on idea of how can I rewrite it so that each of the sub-bits is completely self-contained and can do its own computation, and also how its results can be easily combined in the end. So I think one of the impact of the many-core revolution is a lot of algorithm changes. At the same time, I think the other interesting thing about the many-core revolution is that we're going to probably stop seeing frame rate as like the arbiter of everything. We would start probably seeing, like, people will probably in the near future start talking about latency with the same sort of reference and level of importance as we do with frames per second or frame rate, because in that future the frame rate really isn't so much just important, because if you do an action, it takes a really long time for you to see the result of that action, then it doesn't really matter what the frame rate is. The latency part is very important. So I'm really looking forward to that, because the other thing about refactoring and completely rewriting your algorithm for distributed world too is that you would also start spearheading innovation in like brand new things and brand new techniques you haven't done before, because that world wasn't happening to you before. There were things back then, or in current generation of hardware, which it will be way too computationally intensive to compute that, because fundamentally we have to compute all the subparts relatively sequentially. But then all of those techniques will become possible when all of these processes are running in parallel, and this particular technique is geared towards all these processes running in parallel. I think that's a pretty exciting role.
That's fascinating. Corrinne, thank you so much.
Okay.